Hello everyone, dear students. In first lecture we have seen about the lattice and the basis, and with the help of the lattice and basis how the crystalline structure get formed. Now in this lecture we are going to learn about the translation vectors and the primitive unit cell. Dear students, in 11th standard in physics you have studied about the vectors also and the translations vectors also. Now take one of the example. When a body get displaced or any particle get displaced from one point to the another point along in one directions, then you can say that there is the displacement, or you can say that there is the translation, so that the displacement can be represented by a vector quantity, and that is known as the translations vector. So the basic thing is that what do you mean by that? The translation. A translation is a type of transformation that moves each point in a figure through the same distance in the same directions. So with the help of the translations vector we can move any particle, any point from one position to the another position. Now in first lecture we have seen about the lattice, space lattice. So consider here this is the two-dimensional array of the points. Now if we consider here that the distance between the 2 points along the x-axis, say as the vector A, and the distance between the 2 points along the y-axis, it gets represented by the vector B. If we connect these points, now then there is the formation of a two-dimensional square array. Therefore, these vectors A and B are known as the fundamental translations vector. So with the help of the fundamental translations vector, we can generate a square array in the any lattice space. Then to understand the lattice operation, in case of that, any crystal, how the atoms or how the lattice points get displaced, get translated from one position to the another position, with the help of that the translations vector, we can see it by using with a suitable diagram. Now consider here this is the case of the small group of the lattice points in a 2 dimension. Now in this 2-dimensional lattice space, consider the 2 lattice points get represented by the point A and by the point B. Now let us consider the any arbitrary lattice point, say as the origin O. If we connect the point A with the origin and the point B with the origin, now then OA represent the position vector of the point A, that is OA is equal to the vector R, and the position vector for the point B is get represented by that vector OB is equal to be vector R dash. Therefore the coordinates of the point A are the twice A and the B with respect to the origin. that means this 1a, 2a, so here this is the distance, so it having the x coordinate the twice a and it having the y coordinates only the b. Similarly, the coordinates of the b are the thrice a and the thrice b. By using the translation vector, as we go from the point A to the point B, now then it gets represented by the vector t by using the law of the vector triangle. The OA plus AB is equal to the vector OB. Therefore, the vector R plus vector T is equal to the vector R dash. Here, vector T is called the translations vector. Therefore, the translation vector is the distance through which an atom must be moved or the translated in order to be in the next unit cell. That means in this diagram, we can translate the one point from A to the B through this translations vector T. And hence, the T is known as the translations vector. Now, from this figure we can write the vector R is equal to be the twice A plus B and the vector T is equal to be vector A plus twice B. That means here this is vector A along the x-axis and this is the 2b along the y-axis. If we substitute these values in this equation, so we get vector R dash is equal to be the thrice A plus thrice B. Therefore, in general, now we can write the equation for the translations vector with respect to the origin is the T is equal to be the n1 vector A plus n2 vector B. Now here n1 and n2 are the integers and the vector A and vector B are the fundamental translations vector. Now instead of the point A and B, if we consider the another points P and Q with respect to the origin, then the P having the coordinates 1 and 2. So here this is the 1 and here this is the 2. Q having the coordinates, so the minus 2 and the y minus 1. Therefore, the translation vector for the point P is given as the T is equal to be A plus twice B, and the translation vector for the point Q can be expressed as the T is equal to minus twice A minus B. We can start from the any point, not necessary be a lattice point. Therefore, in case of that, in this space lattice, we can translate the atoms or the unit cell from the any point, and it should be not necessary, it must be a lattice point. Now here in this figure, we can consider such a point say as the x and the y. Now these are not a lattice points here. So the x is here and the y is here, in between these two lattice points. Therefore, by using the translation operation, so we can write here this is the r dash is equal to the vector r plus vector t. So we can express that the vector t is equal to be the a plus 2b. That means a means here this is from this point to this point. So here this is the a by 2, here this is the a by 2. So it becomes, that means x coordinate becomes here this a and the y coordinates become this is the twice b. Therefore, and also here this is r dash is equal, therefore that r dash we can write here this is the vector r plus the vector a plus twice b. Thus in going from R to R dash we use the translation vector. That means basically the translation vector is useful in a crystal lattice when we go from one point to the another point. Therefore, there is the translation operation, and the translation operation we can define. It is the operation, or it is defined as the displacement of a crystal by lattice translation vector. So the displacement of a crystal, displacement of a unit cell, displacement of a atoms by a lattice translation vector, and that is known as the translation operation. So the lattice translation vector is very important in case of the translation operation. So this is one of the example. If we apply the translation operation from point A to the point B, now then in this case here we can write the expression for the vector R dash is equal to the vector R plus vector B. Therefore, by using the law of vector triangle, vector R is equal to B. Now we can write here, this is the twice A plus twice B. That means here along the x axis A, and along the y axis here this is the, along the x axis here this is the twice B. And the T is equal to, as we go from A to the B, now then we can express the expression for the vector T is equal to the A minus B. Therefore, if we substitute the value of the vector R and vector T, we get R dash is equal to be the thrice A plus B. That means here this is the R dash is equal to, we can write here 1, 2, 3, this is the thrice A, and here this is the 1B. So here as we go from the point A, lattice point A to the lattice point B, then by using the translation operation we can write the vector the R dash is equal to be the thrice A plus B here. Now the fundamental translations vectors, vector A and the vector B, can be chosen in a number of ways. Means if we consider the any space lattice, now then in that space lattice these fundamental vectors A and B can be chosen in a different way. Now two such ways are shown in this figure. Now here in figure this is the one, here this is the A1 and the B1, and in this figure A2 and B2 are the two sets of the fundamental vectors. Now in these figures, so what happens here? Now this is vector A1 and vector B1 by using this. Now initially we can, in first lecture we have seen that the fundamental translation vectors can used to generate a square array. Similarly here these fundamental vectors are used here to generate the parallelogram. So here this is the one of the parallelogram and this is the another parallelogram. Now in this case here, that means here this is the A1 and B1 are the sides of this parallelogram, and A2 and the B2 are the adjacent sides of this parallelogram. Therefore here this A1 and B1 are known as the primitive lattice vectors, and A2 and B2 are known as the non-primitive lattice vectors. Now then we are going to see about what do you mean by the primitive lattice and what do you mean by the non-primitive lattice. Now in case of that, here this is the A1 and the B1, the fundamental translations vectors which forms the unit cell, which forms the square array or which forms the parallelogram which having the minimum area. That means all these lattice points are at the corners. Now then these two fundamental translations vectors are known as the primitive lattice vectors. While the parallelogram which formed by the fundamental translations vector, in which there is the some lattice point inside that parallelogram or inside that the figure, then such a type of the fundamental translations vectors are known as the non-primitive lattice vectors. Every lattice point there exists a pair of the translations vectors which satisfy the following condition. So if we apply the translation operation for this space lattice, then the general expression for the translations vector is the T is equal to the vector T is equal to the n1 vector A and n2 vector B. Now here the n1 and n2 are the integers. Okay. Now then from this equation, the value of an n1 and n2 also decides which are the primitive translations vectors and which are the non-primitive translations vectors. So if n1 and n2 are the integers, now then these fundamental translations vectors are known as the primitive translations vectors. But for the every lattice point, there exists a pair of the translations vectors which do not satisfy the condition such as vector T is not equal to the n1a plus n2b, and if the n1 and n2 are the non-integers, then such a vectors are called the non-primitive translations vector. Therefore, it is necessary for the primitive translations vector, it should satisfy this condition of the translation operation. And in case of that, the non-primitive translations vectors, it doesn't satisfy the condition of the translation operation. Now in this figure, we can see that the two-dimensional primitive translations vectors. Now in case of here, in this figure, now this vector A and the vector B, now these are the primitive type of the translations vectors which satisfy this condition of the translations vector. But now in this case here, now these fundamental translations vector A and B doesn't satisfy the condition of the translations vector, and so it forms the cell which doesn't having the minimum area. Or you can say that the some lattice point is inside that unit cell, but now and due to that it is known as the non-primitive, and due to that these vectors form such a type of that the unit cell are known as the non-primitive vectors. But now in this case here, all these lattice points are the corner, so it having the minimum area. So such a type of that the figure formed by the vectors are known as the primitive types of the vector. The same thing is in case of that the three-dimensional lattice structure of the three-dimensional unit cell. If A, B, C are the fundamental translations vectors along the x, y and the z axis, now when these three vectors satisfy the condition of the translation vector, now then there is the formation of the unit cell which having the minimum area. So it having the minimum area, all the lattice points are at the corner, and hence such a type of the translation vector are also known as the primitive type of the translation vector. Now once you know about that, what do you mean by the primitive translation vectors and what do you mean by the non-primitive translation vector. So now we are going to see in details about the primitive and the non-primitive unit cell also. A crystal structure is defined in terms of the geometrical arrangement of the particles in the unit cell. Now here, now this is the figure. Okay, now this is the block. Now which contain the different unit cell. So here it is the block, or it is the building block of the different unit cell. So here this is the one unit cell, second unit cell, and like this here. So here this structure we can describe in terms of the geometrical arrangement of the particles is the unit cell. So now here this one unit cell, it is nothing but the geometrical arrangement of the particles. So the unit cell is defined as the smallest repeating the unit having the full symmetry of the crystal structure. Or in another way you can say as the atoms or the groups of the atoms forming a building block of the smallest acceptable size of the whole volume of the crystal is defined as the unit cell. Or you can say that the unit cell is the smallest repeating portion of a crystal lattice. A unit cell is the smallest portion of a crystal lattice that shows the three-dimensional pattern of the entire crystal. So now in this case here, this is the, in this figure we can say that this is the two-dimensional unit cell, and here this is the three-dimensional unit cell. So here this is the, now here if we connect these lattice points, so what will happen here? Now these four lattice points, so here is the formation of the one unit cell in a two-dimensional. Similarly in this case here, that means if we connect these 8 lattice points, all having the repetitive arrangements, having the equal neighbors, and it forms the unit cell in a three-dimension. Now then here we are going to see what do you mean by the primitive unit cell and what do you mean by the non-primitive unit cell. So now in this space lattice, now consider here that A1, B1 and A2, B2 are the fundamental translation vectors. So now in this figure we can see here the fundamental translation vector A1 and the B1 form the square lattice. So it having the minimum area, so all these lattice points are at the corner. In this figure we can see here, this is the parallelogram which having the minimum area. So all these points means lattice points are at the corner. So here you can say that means the unit cell A.B.C.D formed by this translations vector. So such a type of the translation, fundamental translations vector are the primitive fundamental translations vectors, and the primitive translations vector used to construct the unit cell is called the primitive unit cell. So here this A.B.C.D is the primitive type of the unit cell. Now in this another figure, KLMN, if we use the another, the fundamental translations vectors A2 and the B2. So with the help of this A2 and the B2, it forms the parallelogram KLMN. In this figure we can see that there is the one lattice point at the center of this figure, and due to that we can say that A2 and B2 are known as the non-primitive translations vectors. And if the non-primitive translations vector used to construct the unit cell is called the non-primitive unit cell. Therefore, here this KLMN is known as the non-primitive type of the unit cell. Similarly, in a three-dimensional lattice, the unit cell are of the parallelopi. The primitive unit cell in a three-dimensional space is formed by the primitive translations vector A.B.Sc, which having the minimum surface area, and all the lattice points are at the corners. So, this is the three-dimensional primitive unit cell which forms by the primitive translations vector A, B and C. Now, here we can again see that this is the two-dimensional unit cell. Now here this is the three-dimensional unit cell. So the primitive unit cell is of the minimum area and all the lattice points belonging to lie at the corners only. Therefore, the effective number of the lattice points in this unit cell is 1. Then how we can find the total number of the atoms per unit cell or the effective number of the atoms per unit cell? So here at these four corners, the 1/4 atoms it get contributed in this unit cell. So here this 4 multiplied by 1/4, it is equal to the 1. So the total number of the atoms per unit cell in this two-dimensional primitive unit cell is the 1. Now in case of this two-dimensional primitive unit cell, now here the 8 corners, and at these 8 corners 1/8 of the atom is get contributed in this unit cell. So we can find the total number of the atoms per unit cell. Here is the 8 multiplied by 1/8 is equal to the 1. So here also in case of the primitive unit cell, the effective number of the lattice is 1 only. But now in case of the non-primitive unit cell, this is the 3-dimensional. So what happens here? Now the 4 lattice points, the 8 lattice points are at the 8 corner and 1 lattice point is at the center. So here the total number of the atoms per unit cell is equal to the 8 multiplied by 1/8 plus 1. So the 1 plus 1 is equal to 2. Therefore, the total number of the atoms per unit cell in the non-primitive unit cell is always greater than the 1. Okay, thank you.